In this video, we gonna to prove that the center Z of group G is a subgroup of group G. So we will prove this one. So the first thing we need to prove that the center Z is non-empty set. So we have G is a group and G is non-empty set. So by the definition, since the center is contain the element of G, so that's why Z is non-empty set. Okay. The second is we need to show that Z is closed for products. So takes any AB in Z where A is equal to x1 Z1 and B is equal to x2 Z2 and then we have A times B is equal to x1 Z1 x2 Z2. Okay, so by the definition we can swap Z1 and x2 because in here center is defined by Zx is equal to xz. So this is commute. So all the element of Z is commute, so we can swap. So we have x1, x2, and this is Z1 and Z2. So this is by the definition. Yes, because the elements of Z commute. So we can write x1 and x2 become x3, and this is become Z1, Z2 become Z3. This is elements of Z. So that's why Z is closed for product. The third is we need to show that Z is also closed for inverses. So take any A in Z where A is equal to xz, and since G is a group, then we have X inverse and also Z inverse element G, so in G, and we also have A inverse equal to X inverse times Z inverse in G. So then we get A times A inverse is equal to xz times X inverse Z inverse. As we know, Z is commute, so we can write as X inverse Z inverse. So this is equal to identity. And how about A inverse A? We have X inverse Z inverse XZ. So this is because the center is commute. The center commute. So that's why we can swap Z inverse with X. So we have X inverse X Z inverse Z. This is also is equal to E. So Z is close for inverses. So that's why we can conclude that Z is a subgroup of G. So this is the end of our proof. Thank you.